So this week, I'm very happy to introduce Sidney Nagel. So Sidney's a professor from the University of Chicago. He's well known for his work on complex dynamical systems and fluids and flows and high-speed photography of splashes and things like that. But he's worked on a wide range of physics, often sort of explaining why everyday familiar phenomena are physically very interesting and have interesting physics explanations. So he gave us a bunch of different ideas for what he could talk about today, and we chose the one that seemed the most different from anything that we'd heard about before. So he's going to talk about aging of materials. So it's all yours, Sidney.
Okay, thank you so much. Let me get this. Oh, there we go. Yeah, so thank you for the invitation, and I'm very glad to be able to tell you about our work. What I'm going to be talking about is exploring the intersection of three topics or three ideas. One of them, which is aging, another is memory formation, and the third is greedy algorithms. And so you'll see how I'm trying to bring these together throughout the talk in new ways. What I'm going to be really emphasizing is that in disordered systems, there are new principles. That is, you don't want to start thinking about a disordered system as a perturbation around a ordered one, and that you really want to take a disorder in as a starting point. And so if you do that way, then you can you find that disorder is actually quite malleable, and that you can actually use it for various topics, and that's what I'm going to be trying to emphasize in this talk. So the first part of the talk, there'll be three parts, is our disordered world. And I want to talk about how disorder is inherently different from crystals, and that there are new laws in this. And if there weren't new laws, if there weren't anything really truly different about a crystal, a glass from a crystal, then you would ask, well, why do you really care about disorder? I mean, disorder is, you really want to see what is intrinsically different, and you have disorder, and there are whole new ways that the disordered material can behave, and you want to try to understand that. And so to just start out, I just want to compare the two, crystals on the left and glasses on the right. And the first thing that you probably know already is that the structure of the crystal is, almost boring. That is, it's repetitive. It goes on and on and on. It's perfectly ordered. That once you have your unit cell, you just repeat that over and over and over again throughout space in all different directions. And associated with that is the fact that the ground state for the crystal is very deep. That is, there's a well-defined ground state, and as you would have, let's say, if you had a magnet, it would be a ferromagnet, what either spins up or spins down. And this is the very low energy lying state, and this is where the system ends up. But if I look on the right-hand side and I look at the glass, I see that the structure of the glass is really quite different from that of the crystal. The crystal, the way I've drawn it here, is this perfectly ordered system, and you see in all these orange particles that there's no order in here whatsoever. That is, these particles have kind of been put down, and they're almost at random, and they don't have any short range. There may be a little bit of short range order, but certainly no long range order in this. But if structure were the only thing, then it would be kind of boring. So what else does glass do for you? Well, if you look at the energy landscape and compare that with the crystal, you see something which is maybe pictorially represented by what I have on the right here, but you should be well aware that this is a vast, vast, vast oversimplification. I can only draw the energy landscape for a system like this in two dimensions. And so, you kind of see this rugged landscape. But remember that if I really wanted to talk about this landscape, it would have a number of dimensions, so 3 dimensions times the n number of particles in the system. And this would tell me the number of dimensions I have to try to describe this very complicated set of particles. But what this picture does kind of indicate is some aspects that we want to concentrate on. And so the aspects are that if you look at this, you see that there are very, very many nearly equivalent ground states for the system to end up in. That is, it isn't one deep one as you have in the crystal, that there are many possible ones, and that the energy barriers to go over from one ground state to the next, to its neighbor, are relatively low. So that what you see is if you set this thing at some temperature, the system is continually exploring its phase space and going over some barriers and getting into slightly lower energy states. And if it manages to do that, then it'll spend more time there. And so slowly the system is going to find the lower and lower energy states of the system. And so this is what aging is. So a system ages by being able to explore the phase space and going lower and lower in that phase space, in energy in that phase space. And so aging is, again, something that you would not have seen in a crystal, because the crystal, there's no place to age to. It's already in its low energy state. And the glass is a situation where, because it's out of equilibrium, it can continually look for the ground state of the system, the better ground state. So what I want to do is, well, how do we try to explore or understand this energy landscape? And so there are typical ways that we've been taught to do this in the past. I mean, so one way is if you take a system, well, one way of understanding what the system is doing is you raise the temperature a little bit. That is, you give it more kinetic energy so it can look around at a larger region of the phase space, and you can see what energy minima are close by. And so this is one possible way of exploring a landscape. The other way that we've been taught is that you can take this your sample and start shearing it, for example. So if you shear your landscape, your sample, you move the particles around so that they go to nearby, at least along that trajectory, nearby minima, and you can kind of see something about what these minima are doing and how they're related to one another. And so this is kind of the physics of rheology, of how you look at the mechanical behavior of such a system. But what we want to do here is do something really quite new and different from that, which is we're going to try to take a new degree of freedom for this, which is pruning the system. And so this is what I'm trying to illustrate in this bottom right figure. That is, so if I have this network, and so think of these bonds in this network as the interactions between two nodes, these are the particles. I can go in and I can cut one bond. And so this is a kind of pruning. I can go in and I can prune this landscape. And this is another way of asking, okay, so how does pruning this landscape gently, how does this change its properties? That is another way of asking, what's nearby? What can I get to by small changes in what in how I've set the problem up? So this is the kind of idea. So everything I'm going to be talking about is kind of based on this idea of pruning. And so this is where I'm starting from, in a way of exploring the materials and the energy landscape that's associated with them. So just before I start pruning, I want to just remind you of two things, because I'm going to be coming back to them over and over again. And that what we're interested in is a response to compression or shear. That is, these are the moduli of a system. This is the linear response of the system. And these are two of the more important moduli. There are others, but these are the two I'm going to concentrate on here. One is the bulk modulus. And so what you do with the bulk modulus is you take your system and you compress it in all dimensions and inwards. And that costs a certain amount of energy to distort the system by a certain amount. And so the cost of the energy is basically a measure of the bulk modulus, where the bulk modulus is measured what that energy cost is. And so this is, you're changing the volume and you're asking, what is the energy of that system change due to that compression? There's another modulus, which I'll show here, which is the shear modulus. And so I take that initial square system, and I shear it from left to right, as I've shown in the bottom drawing here. And this does not change the volume of the system, but it does change its shape. And so again, if the system is a solid, that you try to put some strain on the system that moves it in this orientation, and it will cost some energy. And the shear modulus is a measure of the energy cost that it takes to shear the system by a certain amount. And one of the things that you should kind of know this is that in all crystals, the shear modulus is basically comparable to the bulk modulus. They're the same order of magnitude. And why is that? Well, if you think about this, what you're doing when you're compressing a system is, I don't know if you can see my hand, but pushing these two atoms together, and they're being repelled by the interatomic forces of those two atoms. If you try to shear the system and you move them with respect to each other in the transverse direction, they're still going to be moving up against the potential of its neighbor. It may be off by a cosine theta, but I don't care about a cosine theta. The order of magnitude is the same. So the shear modulus and bulk modulus of all crystals are comparable to one another, maybe a third or something like this, but this is the order of magnitude that these things are. And so these moduli tell you something about what the interatomic potentials are typically. So what do I want to do here? I want to look at the bond level response of the system. And this is what's happening with this idea of pruning. So what I'm going to ask you to do is think about your material. You take your material and you measure the bulk modulus. So you compress it, you measure the energy. You shear it, you measure the shear modulus. You measure the energy, you measure the shear modulus. So you know what the unperturbed bulk modulus and the shear modulus are of this material, B and G. And now what I'm going to ask you to do is to go in, don't look, you just go in and grab some bond in that material and you remove it. As you prune it, you take it away. And if you do that, then you can measure the bulk modulus and the shear modulus again with this new system, the new system that is removed one bond from that system. And it will be somewhat smaller, but not very much smaller. So there will be a delta B and with the subscript I because I removed bond I. And so it'll be a little bit smaller. So I measure what delta BI is, and I measure what delta GI is. That is, how much did the bulk modulus change when I removed bond I, and how much did the shear modulus change when I removed bond I? So this is how I get that delta BI and delta GI. But now what I'm going to do is I'm going to replace that bond. So I go back to the initial system, and now I remove another bond. So I'm basically going to do the same thing for every bond in the system. I'm going to remove one bond at a time and then replace it. And I'm going to get a distribution of what these values of delta BI are and the values of delta GI. So they're going to be, some distribution of some bonds will take away if I remove that bond, it'll have a bigger change in the bulk modulus. Others will have a smaller change in the bulk modulus, and likewise for the shear modulus. So it's measuring these distributions is what I'm interested in doing. Now, I've said this, and I hope you understood what I'm saying, but I want to just give the example of a simple crystal because this makes it kind of clearer what I'm doing. So if I took a really simple crystal, that is, I have only one atom per unit cell, so the simplest crystal that I could think of, and these identical cells are repeated symmetrically and interminably throughout space. What do I know? Well, if I go in and I pull out one bond, it will change the bulk modulus by some amount. But it didn't matter which bond I pulled out because all the bonds are the same. That is, they are all, have the same effect on the bulk modulus. It didn't matter if I pulled out one or the other, but it's a crystal, so all bonds are doing exactly the same as every other bond. And so for this very simple crystal, one atom per unit cell, you'll get a delta function for this distribution function. That is, every There will be no contribution of delta BI except that one value, which is the average value of the system. That is, so every bond contributes the same amount, and I will simply get this delta function. Now, this is what you would get for the simplest case of this simple crystal. What I'm going to ask now is, well, what happens if I put in some disorder? And what would you think was going to happen? And so, I don't know about you, but my naive expectation before doing this work was that it would do something kind of like this red curve here. That is, it would take that average value, that the delta function, and it'll smear it out a little bit. Some will be a little bit more, larger delta BI, some a little bit less, smaller delta BI, but basically it's going to be the same thing, just broadened a bit. And so one of the questions is this what disorder does to a system? Is this what the, is this the nature of such a system to have a kind of a Gaussian broadening of that delta function? So that's one question we can ask. There is another question, which is, well, suppose I did have this disordered system and it had something like this red Gaussian that I've drawn there. I can ask, well, suppose I look at that bond way up at the top. So this is the most important bond for the bulk modulus, as it created the biggest difference. If I took that bond away, it had the largest change in the bulk modulus. Delta BI was the largest. Okay, so if I take that bond away, I know it by choice, has the greatest impact on the bulk modulus of any bond. But I would have also expected that it might have the largest effect on the shear modulus as well. That is, the shear modulus that is, if a bond is important for the structure, my naive expectation, again, would have been, oh, well, if it's important for the structure, it's important for the structure. It doesn't matter which way I'm measuring it, the bulk modulus, the shear modulus, Young's modulus, anything like this. It should always be an important bond for this case. So that was my expectation, and I don't know whether it's your expectation, but what I want to show you is that expectation is really completely wrong. So what I'm going to show you is what the distributions really do look like for a system that we have put together that's through a process called jamming, but that's unimportant for what I'm talking about today. And so this is a distribution of the delta BIs for that system. And what you see here is it's a little bit of a complicated graph. I mean, the curves are all on top of each other. But what I'm plotting both the distribution of the bulk moduli, delta BI, and the distribution of the shear moduli, delta GI, and modulo a little bit that I'm sweeping under the rug. But basically, these two things are right on top of each other, that there's a universal curve for what these distributions look like. Not only that, it's not a Gaussian around some average value. This is something which has a continuous and very broad distribution. The distribution goes down as close as we can get to 0 in delta BI. So these are simulations. So they go all the way down to 0 as close as we can get. So it's a very broad, continuous distribution. And it has a power law. This is a log-log plot here. So this is not, before I drew the Gaussian on a linear curve. This, in order to show what we've got, this is on a log-log curve. And you see that it's a power law at low values of the argument, delta BI or delta GI. And then it gets cut off by some exponential term at above its average. And what you can see in here is, if you look at the cyan dashed line, it goes through all of this data, and this is the form of that dashed line. And this is something that Daniel Hexner, a postdoc of ours, was able to compute for what this thing should look like. And this is a kind of a universal curve that has this particular shape. But the other thing that is harder for me to show you here because it got many data sets in this curve, is that what we've done here is we've taken little regions of what the value of delta B are, and then plotted delta G for that little region of delta B over and over again for any region of the that we choose for the bulk modulus, for example. And they all look the same. That is, there's no correlation at all between what a bond I contributes to the bulk modulus versus what it contributes to the shear modulus. These two things are almost completely uncorrelated with each other, less than 1% correlation. So this again is quite surprising. It's saying that it isn't as if you have strong bonds in a system. The bond is only strong or weak for a given purpose. A given, in this case, is only important for a given, for one modulus, but not for another. So, for example, if I took away this bond at the top, let's say this square, this X at the very top. So this is a bond that contributed very strongly to the shear modulus. And then I measure the bulk modulus, well, it would be equally likely to be anywhere along this curve. And so the fact that it's anywhere along this curve is suggesting that, I could have, that it didn't matter which bond I chose, they're always independent of each other as to how they're going to contribute to the two different moduli. And this holds for other moduli as well. So these two contributions are uncorrelated. And so this gives rise to what I call a new principle for disordered matter, which is this independence of bond level response. And so what do I mean by that? I mean that different bonds, so bond I or bond J, contribute very differently to each modulus. That means that I have this very broad distribution of delta BI or delta GI from 0 up to its average value. The distribution is broad and it's universal. So that's one thing. The second thing is that the contribution of any bond to one modulus is uncorrelated to its contribution to another. So for example, the contribution to B is uncorrelated with the contribution to G, which is what I was just emphasizing. And so this is what I mean by saying that, okay, now the laws of a disordered system are really different from the laws that I would have gotten if I thought of this as an ordered system. That is, this is not what I would have gotten for a crystal. It's unique to the fact that I have disorder. So this is what the first part of the talk, which was to tell you that I do get different laws if I want to think about disordered materials versus crystal materials. But now what I want to show you is that the idea that you have a disordered system makes it malleable. That is, I can adjust things so that I have new design rules, so that I can make new things out of this and create novel functionality. And so not only is this a new law of materials, but it's a useful law because I get to use it in various ways. And so let me go back to this idea of the bulk modulus and shear modulus again. And I described what bulk and shear modulus do, and so you have that. But there's another modulus, or another elastic property, which you're familiar with, I think, which is called the Poissons Ratio. And the Poissons Ratio is that if you take a material and you pull it along one axis, the transverse axes are going to change their dimensions. That is, typically, you're going to have something which is called a positive Poisson ratio. And so I don't know if you can see my hands here. So I have a rubber band. And so if I take this rubber band and I pull it, you can see that it gets much thinner along the transverse axis. That's a positive Poisson ratio. And that's typically what all materials do. So here, if you couldn't see the rubber band so well, here is a piece of foam that as I pull this, you can see that the foam gets thinner in the transverse dimensions. And so this is what's called the Poisson ratio of material. And basically every material that we know of has a positive Poisson ratio. It's very rare that you can find in nature anything occurring that has a negative Poisson ratio, although it's totally allowed by theory of elasticity. And so what that would mean is that if you take a material and you pull it along one axis, it gets bigger along the other axis. And so here is, if you can see my hands, this is an Obermann sphere. So if I pull it along one axis, you see it expands in all the other directions. And it's like the universe. The universe is a negative Poisson ratio. It's expanding in one direction, and it expands likewise in all other directions in the material. Okay, so this is clearly not normal behavior. And I would say that there are only two examples of something that you are familiar with typically that have a negative Poisson ratio. One is the cork in your wine bottle. Cork in the wine bottle isn't really negative Poisson ratio, it's about 0 Poisson ratio. And that's what you would like. I mean, if it were a positive Poisson ratio, as you push it into the bottle, it'd expand and it would break the neck of the bottle. And so you want something that doesn't change its transverse dimension as you're pushing along, in this case, pushing it into the bottle. And so that's one example. And so that's why cork is used. It's not just by accident that cork is used for wine bottles. The other example is if you take a sheet of paper and you crumple it, and then you pull it apart, you can see that it expands in all directions. And so that's another example of something that you're kind of familiar with that has this negative Poisson ratio behavior. But what I'm trying to emphasize is negative Poisson ratio is weird behavior. That is, it's not something that you typically see. And I'm going on about this because this relates to this ratio of the shear and the bulk moduli of the material. Because if for, let's say, just an isotropic material, that the ratio of G over B tells you precisely what the Poisson ratio is going to be. So this is the curve that I have here. The blue, it goes from, in 2 dimensions, it would go from +1 to -1, symmetric around the average. And to the left, it's blue, which is the normal behavior. To the right, where the Poisson ratio becomes negative, this is what we would think of as weird behavior. And so I'm emphasizing this because what I want to show is that, using the ideas I just told you about, we're able to design things that have weird behavior, things that you wouldn't be able to design otherwise. So how does this work? And so the idea that I want to go into is, remember, I just told you that G over B is the one-to-one monotonic behavior with respect to the Poisson ratio. So what I want to do is, if I can control the bulk modulus independently of the shear modulus, then I could make that G over B go anywhere I want, from very large to very small. But what I just told you about in the first part of the talk was I'm able to do that by pruning individual bonds. So if I start at some point, I start at the arrow. This is where all the, we made a material that has a coordination number of some reasonable amount. And so so we start here. And then what I do is I go in and I ask the computer which bond has the maximum value of delta BI. That is, if I pull that bond away, it makes the denominator as small as possible. But it makes the shear modulus maybe a little smaller, but it'll only go down by its average value, not its maximum value. So G will drop a little bit, but B will drop much more. So I take away this one bond, and I start moving up this curve. That is, so I started, so here it was someplace on the order of G over B was about 1/10. And now I start pruning one bond, and then I prune that, I measure it, I then prune the next bond, and et cetera, over and over and over and over and over again. Each time I remain with that same distribution function, so I can keep doing this algorithm over and over again. And what you see is that this ratio, G over B, shoots up by something over 10 orders of magnitude. This is a log scale on the on the y-axis. And so there's I'm able to change this ratio, G over B, by 10 orders of magnitude if I just take away the bonds with the maximum delta BI. But I could have done any one of those things. I could have taken away the one with the smallest delta BI, or the largest delta GI, or the smallest delta GI. So I can do each one of these things, or I can mix and match. I can do one after another, anything I want. But what you see is I can now tune this material to have any behavior that I want just by removing a few of the bonds. And so this is in a 3D system where it's known to be quite difficult to create a negative Poisson ratio material. And so at the top here, I have something that went up by 10 to the 11 for G over B. At the bottom, I'm 10 to the minus 8 G over B. So this is something like 19 orders of magnitude change in what I have for this ratio of G over B. And so this means that, gee, I can, if I know enough, if I have a computer that can just tell me which bond has the largest delta BI or the largest delta GI, et cetera, I can, without having to look ahead, I don't have to think very hard. I just ask, okay, which is the one that has the maximum? Take it out, go do it again, take it out, do it again, take it out. And so you can do these things fairly rapidly once you get the linear algebra under control. And so you can run this thing, and I can make any value of the G over B or the Poisson ratio that I want. So this would be a positive Poisson ratio down here, and this would be this negative, very weird behavior up at the top here. And so I want to emphasize that what we're asking is the computer, it has an algorithm, but it's a greedy algorithm. It's not something where I had to ask, do you want to raise the energy for a while I, so that you can maybe eventually get to a better state. I'm just doing it downhill all the way. That is, and going downhill all the way is very rapid and very easy to do once you have the your nodes and your the elasticity of your network. So this is something that we can do, and we can create this very bizarre materials. We can create these materials. But this is one aspect of materials. And so you might ask, well, are there other things that we could do? And so that was a global property. That is, if I look at something, I can pull on that, and it's global modulus of the material that I'm dealing with. But you could ask, well, could I do something local? And so here we took something, inspiration from biology. We wanted to mimic what's called allosteria proteins. And so what the idea of allosteria proteins is this idea that you have this protein, which is a big, complicated molecule, and there's a site up here, where the orange circle is, which cannot bind to this region here because, well, it's unable to bind. But if you have at the other end of the molecule, far away, you bind another molecule, so this the activator molecule over here, this changes the conformation of the protein in such a way that now you can bind the sphere over at the right-hand side. So this is one of the important ways in which proteins regulate themselves, is to be able to have this idea of allostery, that you're able to have action at a distance, as you do something at one end of the molecule, and you can have it do something far away that is beneficial for biology in this case. So what we wanted to ask was, well, okay, that's fine for the molecules in biology. Can we do this in our networks? So we take our networks and we ask, okay, could we create allosteric interactions far away from, we take a source and we take a target and we say, I want to make those two things interact in the way that I want. And so that was the goal here. And it's the same idea as what we were doing with the Poisson ratio. That is, we have these things, we can prune the system in such a way that we can get whatever behavior that we want. And so this is work that was done with Jason Rocks, Carl Goodrich, and everything I'm talking about today was done with Andrea Liu at the University of Pennsylvania. And so the idea here is I take this network and I ask you, Douglas, please come here and choose at random, your choice, where you want to put the source. So you told me you put it down here at the bottom. And then I ask you, oh, before you go away, please choose another point that you want to be the target. So you told me you wanted it here. And then I say, oh, before you go away, is there another point you'd like it to interact with? And so you give me a second target, all up to you, your choice as to where you put these different targets and where you put the source. And I can ask you, okay, if I pull the source apart, do you want target 1 to come apart or go together, or target 2 to go together or come apart? You can, again, it's up to you what you want to choose. And the idea here is that we're able to choose to do this essentially 100% of the time. That is, we can just by pruning a few of the bonds. And so here you see the red bonds that are the ones that we took away. This allowed that interaction to take place. And very simply, it induced this allosteric interaction into this mechanical network. Something that, it seems to be incredibly easy to do in these networks, but at the beginning, we didn't realize that it would be so easy to do. So, what we want to do is, well, okay, so you can do this on a computer. You can do anything on a computer. So can you actually make these in the laboratory? And so what I'm showing here is 2 systems that we've made in the laboratory. I mean, we made lots of them, but these are 2. One is in 2 dimensions. And so this was, we took a sheet of rubber and we cut out everything that wasn't the network. And so this was, we used laser cutting to cut these networks out. And on the right-hand side, we created a 3D object with a 3D printer. And here we, again, had 2 points, which we call the source, 2 points, which we called the target. And if you squeeze the source, you could see the target would move as well in the way that you asked it to do. You can make it come apart or go together depending on what you wanted. And so this is non-trivial. That is, as I said, you can do anything on the computer, basically. But here, we're doing this with real materials. And the real materials really have more constraints than the simple computer models. For example, the computer models that I was thinking about and I told you about were just simple springs between pairs of nodes and nearest neighbor pairs of nodes. And so this is all that was included here. In these materials, there's more than that. There's the bonds, and so those are kind of springs. But around each node, there's bending, and so that's included. There's nonlinearity. That is, as you try to bend these things too much, there's no distortion, and these again have give rise to new interactions that weren't there in the computer model. And so the fact that we can actually make these things work in the lab is showing that this is not a small thing, but a quite robust feature of what we can make happen. And so these things are not in this tiny little linear response region of materials, that you can do these things by really sizable amounts, and the system still responds in a according to with the kind of allosteric interaction that we had in mind. So let's see, where is it? So what I want to end this part of the talk with is that this idea of pruning, it works. I was able to make things. I was able to make things in the lab that actually did what I wanted to do. I could make weird materials, auxetic material, negative Poisson ratio materials. I can make allosteric materials, and I can make these things easily because there are many ways of doing each of these things. So the pruning works, but as you might worry about is, well, if I have a really big system with lots and lots of nodes and lots of edges between these nodes, I'm going to need a very big computer in order to handle all these many degrees of freedom. So you can ask, well, how hard is it to scale the system up in size as a number of nodes? But a harder thing for us, because I care about doing this in experiment, is I would need really, really, really tiny fingers to manipulate the material at a microscopic scale. So if I'm really talking about interactions between atoms, my fingers are much bigger than an atom, and I can't go in and I clip one interaction between a pair of atoms at the atomic scale. So can the two problems with the idea of pruning is, can you scale the system size up, and can you scale the feature size down? So these are the two competing things. And so this is the question that I leave here for the end of the part 2 of this talk. And now the third part is I want to show you how we can get around those two problems. And so this is what I call directed aging, and thinking of this as a new fabrication methodology in which I want to get the materials to train themselves so that I don't have to do the work anymore. I don't have to have a computer to do the work anymore. The material figures out what it needs to do and then does it. And so the idea here is that I emphasized at the beginning that aging is a feature of disordered materials. It's a feature of materials that are far from equilibrium. And disordered materials are very often far from equilibrium. And we think of aging as a nuisance. It's a degradation of the properties of the material. So you know this well, that if you have a piece of plastic and you let it sit around for a while, it tends to get brittle. Some plastics tend to get brittle. And so that's aging. And so then it breaks and it's no good. Or a beam that you have holding something up over time begins to sag as gravity works on it, and the system has aged in some way because it didn't start off in its ground state, and so it's continually searching to find where that ground state will be. So this is, the idea that aging is a nuisance. But what I want to do here now is I want to embrace aging, because it's all I've got left for me is aging. So that's where I am. And so I want to embrace aging and say, well, it actually is a useful thing. And so this is where I want to go in this part of the talk. And so what I want you to consider as an example of what can happen. And so there's a Duncan experiment. So you take, an enormous pile of sand or salt or rubble, whatever you have. And you look at this thing and you look deep, deep, deep inside this pile near the bottom. And the pressure from all of the sand or salt on top of it is incredibly large. Right? It will crush you. And so the sand or salt is holding itself there. And so it's on the different grains in there are under a lot of pressure. But if you look at this carefully, you'll see that in some places, like what I have here at the upper right, is that the two grains really have extreme forces between them. It just happened that the forces from all the pressure around this thing were really pushing in at that, along that axis. And so the two particles are really smushed up against each other as much as possible. Whereas a little bit farther away, or another pair of bonds on that same particle, the pressure isn't so large. That is, that those particles are not particularly feeling the forces from the ones above, and so they hardly interact at all. That is, it's just normal interaction that is just slightly touching one another. So this is what we have, and so deep inside this pile. And I ask you to consider, well, what's going to happen in this case? So after a very, very long time, the particles that are under a lot of stress are going to start to deform. So if you have this pile and you let it sit there for a century, and you just let this thing sit there, so the particles that are really pushing against each other, they're slowly going to deform, and there's going to be plastic deformation at the contact. Whereas the ones that didn't have any particular stress on them, aren't pushing into each other, and there's no reason for them to deform. They're not going to be aging, particularly because there's no forces on them. So the aging over time is very similar to this idea that I have been telling you about before of pruning, that as a system evolves, that is, as it ages, the contacts that are under the most stress are going to deform or evolve, and those that are under no stress or very little stress, they're not going to evolve. And that's what we did with the pruning. That is, we asked which bonds were under the most stress, and we pruned those. Here, we're not pruning it. We're letting nature undergo its aging process, which is the plastic deformation, and this is going to allow the system to manipulate itself. So what we've done here is we're letting the stress on the material itself. We applied the stress, and the stress is going to direct or dictate how that material is going to age. We do not use the computer to optimize the response. We're just letting the system do it by itself because it knows which particles are under stress and which are not. And I don't need to go in and do any with tiny fingers to do any pruning because the material is plastically deforming on its own. That is, it didn't need me to go in and help it along. What it needed was to know what the stresses were that were applied from outside, the external stresses, and now it's only trying to respond to those. And it has a memory of what those stresses are, and that's where this idea of memory comes in. This idea of memory is what directs the aging process as it goes along. So how do we think about this? So we can do this in a simulation to show how this would work. And so if you take any network of the kind that I was telling you about, the energy is just the energy of all of the individual bonds. So I sum over each bond I, and it's 1/2 k delta x squared. I mean, so it's the length of that bond minus its rest length squared, and so that's what the energy is of the system. Okay, so it's just a sum of springs, spring interactions. And then what we're asking is, okay, because this thing is under stress, whatever stress we put on the system, I can let the spring constants evolve in time, so that the spring constant, if it's under a lot of stress, maybe that spring constant is going to get weaker in time. And so then it'll get weaker corresponding to how much energy is involved in that particular bond. And so dki dt is going to be proportional to the energy in that bond. And so it's going to get weaker over time. I could have also done another model where I say, okay, because these things were, let's say the bonds were compressed, well, over time, those bonds are going to slowly change their equilibrium length. So Li0, the equilibrium length of that bond, is going to slowly change as time goes on in such a way that it lowers the energy of that bond. So if the bond were under compression, Li0 would slowly get smaller as time goes on. And so the aging is just minimizing these energies. And so you can put this into a computer simulation and watch what happens. And so this is what Daniel Hexner postdoc did. So started with that energy. And so he's, in this case, he is using just letting the spring constants vary slowly with time. And as you slowly age this material, the Poissons ratio, which started out as a very nice, hefty positive number, almost 0.4, goes down to close to minus 0.3. So we go into this very negative Poisson ratio regime, and where materials are hard to form, but we can make these happen automatically. We can make the materials do it themselves. Okay, so again, as I say, you can do all this stuff in the computer. Can you really make this happen in the lab? And so these are a bunch of examples of materials that Nidhi Pashina, who is a graduate student who's just taken a postdoc at Yale just the past month, did. So she took this EVA foam. So it's a foam kind of like the foam that I showed you earlier. And she cut out everything that didn't look like the sphere packing, or she took in the middle one, she made a network where each node was the center of these spheres, and then she just had the edges being the where there were contacts between particles. Or she could do this last one, which was everywhere there was a particle, she just took the particle away. So she's just left with the anti-particle. And so these are three very different things. Well, they're all based on the same kind of packing of particles, but they're clearly very, very different from one another in what their response would be. And so all she did was she took these materials, and we wanted to lower the bulk modulus in order to get a negative Poisson ratio material, right? That was what we said in that early case where I first told you about pruning. We want to lower the bulk modulus as much as possible without affecting the shear modulus. So what she did was she took these materials, and they had some initial size. She squeezed them and put them into a box. So this black region is this box. And she just left it in there for a day. So aging time, sometime tau. And without doing anything to this material, just let it sit there for some aging period. She then removed it and was able to then measure the Poisson ratio of that material. That is, she could take this thing and squeeze it and see whether the sides moved in or moved out. So this is what her experiment was. And this is what the results were. So what she found was that in all cases, so these are these different jam networks, jam packings and networks, the holy sheets that we have here, all of them, as the training strain increased, the Poisson ratio dropped dramatically. And in the two of the cases of the network and the holy sheet, it went significantly negative. So we got down to -0.6 and -0.35 for these things. So really in the very negative Poisson ratio regime. And this depended on what was the strain that we put this under. So if we only squeeze it a little bit, it doesn't really age very much. As we strain it more and more and let it sit under that aging, you see that the over time the system really develops this the negative Poisson ratio that we want to demonstrate that you could do. Again, a very weird property, but now it can be done pretty robustly in these materials. So, what is the just to conclude here is that glassiness. The first part of the talk was trying to emphasize that glassiness is very, very different from crystallinity, not just in the structure, which is perhaps the boring aspect of it, but in its properties. That is, it really is has other features which need to be explained. And what I pointed out was one of the things that it had was this this independence of bond level response. So this was a new way of thinking about how materials behave. Then I tried to show you, well, given that, we can explore the landscape in new ways. And so you can either do it by pruning, which is the second part of the talk. We prune these materials and you were able to get to new features, new functionality, or you could train them via the directed aging. And in these cases, it wasn't very difficult to do because we only use greedy algorithms to minimize the energy in either computer algorithms or nature. The idea of directed aging was one where you have a memory of the history of the material, and the nature itself detects the landscape and it just minimizes the energy. It goes downhill, and it does so without the computer. And so these are the aspects that I wanted to kind of conclude with here. But I actually don't think that any talk is really done until you've actually exposed the bullshit line. And so this is the bullshit line. So everything below here is up to you whether you want to believe. Everything above here, I think, I've tried to say, give all the arguments why it really is true, and these are real results. But now is the bullshit line. So what are the things? What does it make you dream? What can you speculate as to what you can do with this? And so this is where I want to just end up. And so there are a few things that you can think about. One is that you can make materials that perhaps have many different possibilities. That is, you design for many different goals, not just one goal. You can have one goal and then you decide you don't want that goal anymore and erase that goal because it's it's stored in the memory. And if you can erase the memory, you can go back to its initial state and train for another goal. Or, as I showed in the case with the Alsteri, I could train several different things at the same time. But the important thing here is not only that it's pluripotent, as you can do all of these things, but you can do it in situ. That is, I didn't have to think about this before I deployed the material. I could put it out in the field and say, oh, this is what you want. Okay, so now we apply strains of a certain kind, and now the material is going to deform according to those strains and create the functionality that we want. That is, it's what we like to think of this as it's a kind of a mechanical equivalent to a stem cell. That is, stem cell can do anything, but it needs the triggers. Once you've given it the triggers, then it starts developing in certain ways. And so we think of this kind of as a stem cell-like mechanical material, if you will. The other thing about this is it's scale-free. That is, I talked about atomic glasses, perhaps, but there was nothing particular that had to, there's no place where size really came into this. So I could go from the glass scale all the way up to the architectural scale. So, for example, a lot of architecture these days, I mean, in the past, architecture was always done on these rectilinear kind of grid-like patterns, and so kind of like crystals. But more and more, as architects like Frank Gehry make oddly shaped, structures, you're really starting off with a architecture which has a very a random direction of these of this underlying structure. And so you can think, oh, well, if it's this way, then I can begin to train it. I can train it for functionality in a building that I didn't have before. I could train this building, for example, to try and become auxetic. If it feels a wind, it can try to strengthen one part versus another part, or if it feels an earthquake, it can do something like this. My own particular example that I would love is to be able to have at work, if my colleague across the hall gets me irritated and pisses me off, I want to be able to go to my window and push it out just a little bit and have his window fall out. I mean, this would be a perfect example of using this for a way of using architecture, new functionality that allows new functionality that you hadn't thought was possible before. Of course, we started off with the Alsteri, and this was mimicking biology, and so here we want to imitate biology more. And biology is incredibly complicated with all sorts of wonderful things. It has molecules that can actually do the pruning for you. It can prune the most stress bonds or the least stress bonds in different cases. And so that's actually something that maybe we can think of some of those processes as the kind of pruning that we're doing in these mechanical networks. And the final thing I just want to say is that, all around us, we have memories, and it's ubiquitous. I mean, and so, and things are repeated over and over again. So the sun comes up roughly the same time every day. The lights in your house go on roughly the same time every day. Your heart is beating roughly at the same rate all the time. Your breathing is at the same rate. And so all of these things are somehow encoding some kind of memories in the material that it deals with. And these memories are all around us, and they're encoded. And the question that I have, which fascinates me, and I don't know how we go about doing this in well, is, but can we read them? I mean, can we go back and, by looking carefully at the memories that are encoded in materials around us, can we see what our history has been? And so with that, I just want to say, again, who are the people who I highlighted throughout the talk who did all the work? And so I mentioned Andrea Liu. She has been working with me for many years on all of these projects. She's at the University of Pennsylvania. And then Carl Goodrich was her graduate student who started all of the pruning work. Daniel Hexner was our postdoc at Chicago who showed how we could make these things work. Jason Rocks did the allosteric interactions. He's a graduate student with Andrea. And then Nidhi Pashina and Irmgard Bischofberger are the two. Nidhi was a graduate student, Irmgard a postdoc, who did all the experimental work. And with that, I would like to stop and thank you for inviting me. Thank you.
Right, thanks very much, Sidney.